So how do you do error estimation, and how do you use these in a marking strategy? Well, there's a number of different ways to do error estimation. The one I'm going to look at here is based on what's called the nonlinear residual. This is sort of a class of error indicators that are based on the following, for nonlinear problems, which are based on the following observations. It's sort of a three-line lemma, three-line proof to a lemma that you can relate the error in the solution to a nonlinear problem by something that looks like the condition number of the linearization around the solution times the nonlinear residual. This is actually not computable, but you can compute an approximation to it. And so error indicators are based on computing approximations to this guy here. This is just some notation if we wanted to examine the structure of these error indicators very carefully, but I'm not going to focus on that. I'm just going to say a couple words about this nonlinear residual indicator. Do I have... Okay, so maybe I'll just point to this thing right here for a minute and I'll jump back. So if we have a local indicator that's produced on each element, T, in a triangulation, and then I have a sum over all the triangles to produce a global indicator, then this is what I meant by being able to use the residual as a way to bound the error using this sort of simple linearization type idea. And so in other words, what these little local error indicators do is bound this from above by some computable quantities. And so that's what I've written down here. Now what I have here in these other slides is just a sort of a more drilling down into each of these steps of this adaptive refinement procedure: solve, estimate, mark, refine. So the solver strategy I'm not going to talk about here. It's based on Newton iteration and using some fast solver for the linear problem that arises. And we have a lot of work on how you solve these linear problems that come up in these semi-linear situations using fast techniques like BPX and stabilized hierarchical basis methods. So we have some papers on how you show that these are linear complexity solvers for this setup. Okay, and then the estimate step is based on doing a residual calculation. So this is basically looking at the strong form of the nonlinear problem locally, and then some jump terms across all the element boundaries in the domain. And then I'm sort of ignoring a possible boundary condition here. And then there's an oscillation term that appears really just in the analysis here. We don't actually compute this. Okay, and then the marking strategy is based on what's called Dörfler marking. And so basically we just mark some fraction of the elements to guarantee that we get error indicator reduction. The refinement strategy is a standard thing. We do some sort of bisection procedure, which is guaranteed to be non-degenerate. Okay, and so I just want to say a couple words about how you then prove something about this algorithm, given that you're going to do this fairly standard error indicator and marking type decisions. So one of the things you can show using this kind of error indicator is that you get monotonicity. So if you enrich the space, you can only improve the error indicator, so it can never grow. And then also the nonlinear residual dominates the oscillation term. And then you can prove these global upper and lower bounds. These are very standard, and you can find these, for example, in their first book for this type of residual indicator. So this is basically a global upper bound and a global lower bound, and this is almost sort of a norm equivalence statement between the error indicator and the energy norm. Okay, so given that setup and this marking strategy, for this algorithm applied to this class of semi-linear problems, we can prove the following contraction statement. And so basically, as a measure of progress, we have the error in the current approximation at step k plus 1 bounded by the error in the approximation step k, where also we have the indicator as part of the metric. So the sum of the two decreases in a contracting way. So alpha is some constant strictly less than 1. And the way you prove this, so this is basically what we're after. And if we have a statement like this, and we know quite a bit about the details of the steps of the algorithms, what the complexity of the different steps are, then we have a hope of actually showing that this kind of an algorithm is optimal. And so the way you prove this, it's a variation of a recent paper by Cascon, Cruiser, Nochetto, and Siebert for the linear case. And what their proof uses is the simple Dorfer marking strategy, the sort of trivial inequalities I had on the previous page about domination of the oscillation by the residual and monotonicity of the indicator. The global upper bound, which is a standard result even for the nonlinear case. And then we needed a variation of what's called an indicator reduction lemma, which I have on the next slide. And then a second new piece was we needed to establish a quasi-orthogonality lemma, which I'll explain what I mean by that in a second. So I'll come back to that, those two things. So there are two pieces of the theory that need to be sort of put together in order to prove that theorem. So if we have this contraction result, then I'll just say what I mean by optimality. So there's some technical assumptions we have to make about the data in order to say exactly how good we can approximate the solution to this problem, and characterizing this class of data in the solution space is actually a sort of a non-trivial problem in approximation theory. But so I'm just going to define it like this. This is sort of the standard way to think about optimality in this setup. So what you can show is that given this contraction type inequality for the algorithm, you can show this optimality result. And this is, you can show that for data in this approximation class, this is the best you can do. And this algorithm realizes that due to this fact that we have the contraction inequality plus some details of the complexity of these refinement procedures that we use. Okay, so the two missing pieces are then we have to establish this nonlinear local perturbation result that sort of feeds into this nonlinear indicator reduction. It turns out the proof of this is almost a linear case, and it rests on this set of inequalities. And then so our paper on this is the work is basically establishing this thing here, which I won't give you the proof of it. I'll point out where this is, where you can find this. But one key thing here is it depends on being able to show that the data, and in particular the continuous and discrete solutions to the problem, are bounded in an interval. So basically what I have to have up front about the solution to the problem before I can say anything about the way these adaptive algorithms are going to work is that I have to have a priori L-infinity bounds for the solution to these semi-linear problems. And in fact, this is the second place this is actually appeared. I mentioned that we have to have a priori estimates of some type to get this Lipschitz type inequality for the semi-linear term just for linear approximation, and it's the same type of inequality. I need a priori L-infinity estimates for the solution, both the continuous and discrete solution, in order to get this Lipschitz type inequality. So basically everything in the linear approximation case, and then also finally these lemmas that we need for the nonlinear approximation setup, rests on having control of the nonlinearity through L-infinity bounds. Okay, and then the last piece is I need some notion of quasi-orthogonality. I just want to explain what this is, because this is sort of the core idea in these contraction arguments. So now we have this semi-linear problem. We can think about this as an abstract weak formulation that these semi-linear problems come in. I'm going to assume coercivity and boundedness, so this is something like the Laplace or Laplace-Beltrami operator. And then I'm going to assume again that I have this Lipschitz property of the nonlinearity, which I'll get through a priori bounds on the solution and the discrete solution. Okay, and then the discrete solution satisfies this in the discrete space, so the continuous solution satisfies this. Here are the Galerkin equations. And then if I have an enrichment condition, this is sort of the standard type of inequality that you would use to do an Abenishi type argument. So you typically need some sort of additional regularity to have an inequality like this that says you make progress when you look at a stronger norm versus a weaker norm on the approximation space. So given that you have this inequality, and then you just have the basic information you have about the continuous and discrete Galerkin equations and a priori estimates, then you can establish this inequality. So it's not orthogonality, right? There's a constant here, and this is only an inequality. But it turns out you don't need orthogonality to prove contraction for these types of algorithms. You only need this inequality. So this is referred to as quasi-orthogonality. The constant here depends on the constant here. So typically this depends on the mesh being sufficiently fine. And so this quasi-orthogonality inequality is going to depend on the mesh being sufficiently fine in any discrete setup here. But then that's the whole piece. This is a proof of it, so I'm just going to skip that.